And then we continue with Hugues Auvray, and he's going to be talking about an analytic construction of dihedral ALF gravitational instantons.
Thank you very much. Thanks. I'd like to thank the organizers for bringing me here. That's my real pleasure. And I'll start with an introduction to kind of fix the vocabulary, since there is in the literature many variations on what is a gravitational instanton. Let me at least try and fix this particular vocabulary for the rest of the talk. So I consider a Riemannian manifold Xj, G, and I call it a gravitational instanton if X is non-compact, if it is metrically complete, if G is hyperkähler, and if the Riemannian tensor curvature of G satisfies some L2 condition. And so, which I write this way, where d mu is not exactly the volume form attached to G, but some twisted volume form. D mu is equal to this volume form. Where times volume, where rho here is the distance to a fixed point, which actually does not matter. So this kind of be seen as strengthening the sort of usual L2 condition, the Riemannian tensor.
So in the ALE cases,
it's basically the same, but in the at least as soon as you jump to ALF case, it strengthens the kind of decay you impose on the Riemannian curvature.
The volume with respect to the metric G of that ball, is that what you mean?
Yeah, sure.
with respect to Euclidean, no. Oh, no.
No, the Euclidean, this guy.
And the dimension is 4.
So, as you probably all know, hyperkähler implies Ricci flat, which in turn implies, by Bishop-Promer theorem, Euclidean growth of the ball volume, at most Euclidean growth. So, ball volume is controlled by the Euclidean growth, which would be CR4. So, if this bound is effective, meaning that if you have a similar lower bound, if you are in the so-called ALE regime. ALE standing for asymptotically locally Euclidean. Asymptotically Euclidean. And actually, those particular spaces, those ALE gravitational instantons, they are very well understood, as they are all classified by Peter Konheimer. Who also gives an exhaustive construction by hyperkähler quotient. And just to sketch a picture, let me just say that these spaces are deformations. These all are deformations of the minimal resolution of the Kleinian singularity C2 over gamma. So I denote the minimal resolution by this hat, where gamma is a finite subgroup of SU2 and can be any finite subgroup of SU2. So it can be any cyclic group, binary dihedral, binary octahedral, icosahedral, or tetrahedral. Subgroup of SU2. Okay. So if now the upper bound, the Euclidean upper bound, is no more effective, there is a result due to Vincent Minerbe saying that you directly jump to an upper bound in a cubic upper bound. So if one phase, the ball volume now is at most growing cubically, so it's due to Minerbe. And again, if now this is effective, so you have a similar lower bound, you speak about ALF, instantons. The F is now standing for flat. So you have asymptotically locally flat manifolds in the sense that, and this is a structural result due to Vincent Minerbe again, in my theorem 0. You have a kind of model for your manifold, your complete manifold outside the compact subset, a rather simple model. So x minus k, so k here is a compact, some compact subset. X minus k is the total space of an S1 vibration which I denote by pi over R3 or R3 quotiented by antipody minus a ball. Moreover, the fibers, the length of the fiber tends to some positive constant at infinity, near the infinity of x, and not only you know about the space itself, but you also know about its metric. Your metric G over there is asymptotic to the pullback of the Euclidean metric on R3 plus some squared connection one-form. So where here eta is possibly local in the quotient case, connection one-form for pi. And so let me illustrate the theorem with a couple of examples to make things a bit more concrete. So you have the trivial example, which is just given by R3 cross S1, and here everything is perfectly obvious, but you have something probably a bit more interesting, which is the Taubnet metric on R4, which I will see as C2 in the following. So this is the following description is due to Claude Lebrun. And I see this C2 equipped with the standard complex structure. So the description goes as follows. You pick some positive parameter m, so which I will refer to sometimes as the mass, and you define three functions as follows. So you take yi equal to u2 minus v2 2, where u and v are given by the following implicit formulas. And u2 plus y2 plus I y3 is just the product z1 z2. So here, of course, c1 and z2 are the ordinary holomorphic coordinates on C2. And so with this datum, you can constitute the following metric HM. The one squared plus b minus 1 eta squared, with eta equals to I1 v1. Sorry for the little formulas there. 1 plus 4 and r to r, and r goes this way. So HM will be this Taubnet metric, but the interest of this description is that HM is I1 scalar, so meaning that it is scalar for the usual complex structure on C2, and more precisely, you can write it as DDC for I1 of some potential phi m, and the phi m is completely explicit in terms of these yj functions. And oh yeah, you recover all the ingredients of the theorem. So you can see as v tends to some constant, you can see the asymptotic of the metric. Your connection one form is here. Yeah, the vibration would be given as follows. C2 over R3 is just given by your tripole of yj functions, and so on. And an easy way of checking that HM is indeed hyperkiller is to see it Ricci flat. As C2 is simply connected, this is the equivalent. And HM is indeed Ricci flat as its volume form is nothing but the Euclidean volume form. So which I think gives a particularly nice description of the top-band matrix. Okay.
I don't quite understand the Euclidean volume form
On C2. I'm on C2.
which has chordic volume growth.
No, but the distances are different because it's with respect to
Yeah, the distance, here, the distance is something
Yeah,
like
yeah.
R.
Okay.
It's,
Yeah, it seems like a paradox, but it's not.
Yeah, it's a bit perturbing at the beginning, but you get used to that. So yeah, let me come back to this theorem 0 and underline that
I
obviously.
think the potential phi is just chordic.
Yeah, it's quadratic in the. It's something like R plus M y squared plus maybe with 2 and 4 coefficients, but something like this. So yeah, there are obviously two situations in theorem 0. Either your vibration over R3 or R3 quotient. And so the first situation, R3, is the so-called cyclic case. And in for this manifold, the picture is well understood as these people are classified by Minerve, who takes advantage, who rebuilds an S1 symmetry on these spaces. You have for coordinate. The S1 symmetry is easily seen. You just add diagonally by ei theta on the first variable, e minus I theta on the second variable, and everything is invariant. And the same happens for in the cyclic case for ALF instantons. And also thanks to this S1 symmetry, you have a very elementary description with the Gibbons Hawking ansatz. So now in the other situation, the situation is less clear. So this would be the so-called dihedral case. And so far, there is no complete classification of this this half family of ALF instantons. So there are different classes of examples. So, for example, the Atiyah Hitchin instanton and its double cover. There is the Hitchin space, and there is another family which I will focus on for the rest of this talk. Which is the family of the decay ALF instantons. So such a family has been produced by Sergei Cherkis and Anton Kapustin by moduli space methods. Namely, they build these spaces as moduli spaces, either of solutions of Nernst equation or of singular monopoles, and they had been also reconsidered in a quite, in an explicit manner by Cherkis again and Nagarichin, with generalized London transform and tristorial methods. And for the rest of the talk, I would like to propose an analytic construction of such spaces, maybe to shed a different line on this. And this analytic construction is made out of ingredients such as Collimer instantons, the dihedral Collimer instantons, and the model, the dominant metric. Be the result part. But let me again fix notations, or as this can vary. So I use the script D here to make the distinction between with the usual decay. So to me, decay for k at least equal to 2 is the subgroup of SU2 generated by two matrices, tau and zeta k, with tau this inversion of coordinates with a twist in the sign, and zeta k this multiplication, this diagonal action, by 2kth root of the unity. So 1 pi over k, 1 minus pi over k. And with this convention, dk is always of order 4k, right? And so let me draw your attention to the fact that with the description, with the, so to speak, Lebrun's ansatz of dominant metric, I can see that this metric HM is decay invariant. So everything is preserved by zeta k, and the signs of the yj's and of eta are reversed by tau, but at the level of the metric you don't care anymore because of the squares. So HM is descends to C2 mod decay, which gives you a very good model to start with in a gluing construction. So now the spirit of what follows will be to glue HM on C2 mod decay. We keep it at infinity to Kronheimer's decay ALE instanton. So this will be my theorem 1, A. So let x, g0, I1 of x, 2 of x, 3x be an ALE decay gravitational instanton then there exists a whole family, one parameter family of ALF metrics on A that are modeled on the tablet metric and for which you have extra information. So there exists a family I will call GM J1 of X, so J1M of ALF hyperkähler matrix such that, so first GM for any fixed M. So notice that you can describe the whole range of possible M's here. So GM is for fixed M asymptotic to HM. So this requires a kind of chart at infinity, but I'll come back to that when I will sketch the proof. Just it is asymptotic for some natural chart to HM. Second, your Kähler classes are preserved. So this means that GM of GMJ is equal for any fixed M and all J to G0 IXJ and maybe this is an ingredient of the proof actually. GM has the same volume form as G0. So the volume form is also preserved in the construction.
So in line 2, you're indicating the symplectic forms, the three symplectic forms?
Yeah, these are the symplectic forms. I just didn't want to add up any more notation, but these are the, these are the three Kähler classes for GM and the three initial Kähler classes. Right.
So in one, when you say symplectic, the difference is bounded by some...
The difference goes to 0, and you also have with some rate of decay, and you also have the similar coincidence at for one derivative. Yeah. So as this statement suggests, one of the ingredients in the proof is to build the metric GM with this condition, which, as we saw in Olivier's talk, is typically typically solving a Montampere equation. So this theorem A heavily relies on the following. Theorem B, which is one of the main analytic tools in this construction. So let y, gy, jy, omega y be dihedral ALF Kähler manifold. So I come back to that after the statement, and let f a smooth function on y with some decay as follows, such that there exists some positive beta smaller than 1, such that f decays as rho minus beta minus 2, and similarly for its derivative at any order. Okay, so then there exists some smooth function phi such that the following equation, so that you can solve which solves the following equation: omega y plus ddc y phi squared equals EF omega y squared. And you have, thanks to the decay on F, you have a similar, not as good, but a similar decay on phi. For all positive L, the Elliott derivatives of phi decay as rho minus beta minus L. Okay. And so, before I come to the proof, let me draw a few comments on these two statements. So, first on theorem A, it is, I highly suspect that these spaces are really are the same as those constructed by Cherkis and Kapustin. This construction should be exhaustive, is expected to be exhaustive, but so far I could honestly couldn't prove that this coincide. But yeah.
If you instead rescale these so that m appears to be constant, you get like tau nut as a Gromov-Hausdorff limit, and then as the pointed
yeah.
Gromov-Hausdorff limit, but the rescaled limit is ALE.
Yeah, with a perturbative gluing argument, I think you can really do that. Yeah.
Very nice.
Yeah, my method is a bit brutal, as you would see, but so you at first you can't see it, but I think it really is doable. And this is what notation suggests. In the other way around, if you let m now tend to 0, you should get the AV instant. So that was first comment, and now on theorem B, there is so yeah, as I said, this is a Monge-Ampère equation, so which helps you in prescribing Ricci forms in in Kähler geometry, which is what we are going to try and do to prove theorem A, as we want at the end a Ricci flat metric. And a more or less similar statement has been more general statement, I have to say, is proved by Hans-Joachim Hein, but it's more general, so you don't have such asymptotics. You require less precise asymptotics at the beginning, and at the end you have less precise asymptotics. But I was really needing the asymptotics to get the one statement here, which is why I kind of refined Hein's statement theorem. And as I promised you, now a little explanation about the vocabulary, the terminology here. So what I mean by dihedral ALF Kähler is that y obeys the is a vibration, is an S1 vibration over R3 over Z2, just as in theorem 0, or base case R3 of theorem 0. So of course it is a Kähler manifold, and you require some compatibility between this structure at infinity and the Kähler structure, and at least locally J dy1 is equal to eta, not equal but asymptotic to, and J dy2 is asymptotic to dy3. So I'm hiding a little bit of complicated stuff in the asymptotics here, but this already gives a good picture of what you require on your Kähler manifold. Right. So yeah, these are my theorems, and now if you don't have questions, I'll try and give you a sketch of proofs for both. So I start with theorem A, and to begin with, I consider the case where the ALE instanton is a resolution of the Kleinian singularity C2 mod decay. So assume x y1 of x is a resolution of C2 mod decay equipped with the standard complex structure, which gives me a proper holomorphic map phi, say, from X to C2 mod decay. So it is defined. It is actually defined everywhere, but it's biholomorphic outside of the origin on the right side and outside some configuration of -2 curves on X. So having this holomorphic phi allows me, so first this gives me the somehow natural chart I was speaking about when commenting theorem A before. And second, it allows me to identify those two complex structures at infinity. And so now I'm trying to perform some gluing in Kähler geometry, and the natural way of doing so is to operate at the level of Kähler potentials. So now I can bring back with my phi map the Kähler potential of the tablet metric from this guy to this guy, and then do some cutoff, compute some complex Hessian, and correct. Right? This is the way you proceed in Kähler gluing constructions. So say that. So the first step 1. So omega 0 will be my starting. So y1 is my favorite complex structure on X. And so you start by gluing the tablet metric to phi 0 with help of the potential, the tablet potential phi m put back to x, which does give you a metric because those two, at least when it's the full potential, because those two coincide. Phi m. So you have to use some cutoff and to subtract some potential for omega 0 as well, so which I hide into a little twiddle here. But this is if you are a little careful with the parameters, you can do it quite nicely. And at this stage, what you have is that omega m differs from the Kähler form of the tablet metric by 3 orders, where rho is some distance function for this reference metric. And a surprising fact somehow is that when you take derivatives, you actually don't improve this asymptotics because of the error terms hidden in there, which are, so to speak, Euclidean error terms, and they don't. I mean, and using ALF metrics only allows you not to lose too much, but you won't win anything by differentiation.
So in this computation, you're effectively using rho to be the tablet radius.
Yeah. I would say R as before. And you have this up to 3 orders. One order more is not. I mean, you need to correct more to win more orders. So and this gap between those two geometries, the Euclidean or the ALE geometry and the ALF geometry, does not allow you, especially when m is big, to proceed with to keep Ricci small during the gluing. So basically, you have your tablet space here that you glue with ALE instanton here, but in the gluing region, these things can be very wide, and this is what we want to correct.
What does that scale in terms of the metric rho? I mean, where is the gluing region? Is it fixed or is it changing?
Yeah, it's I don't really remember, but it's very, very far, and it's huge. It's you first need to fix. I don't quite remember the details precisely, but
you're doing the gluing for fixed m.
Yeah, the gluing works for fixed m, so you don't control much. You don't control much. You control when m is in a fixed range, far from infinity and zero, but in the limits, it's really non-perturbative argument.
So do you have to presume that the resolution parameters of the ALE are less than 1 over m?
Sorry?
Do you have to presume that the resolution parameters of corresponding ALE are less than 1
No,
over m?
no, you can really do that for any ALE guy, and any tablet metric, with any mass.
Do we scale it so that
No, you.
still out and
He's got a fixed scale because he's chosen m.
yeah, so m fixes the asymptotic at infinity that
Yeah.
we want, and then
He also has
resolution
a
tells
fixed
us
scale class, so-
how big the core is. So, I mean, back to Rafe's question, where would we place this transition region?
Yeah, it can be. I mean, it's typically very, very large and quite far away from. Yeah, it's more like.
So if I understand it, I mean, you're fixing these Kähler classes too, right?
Yeah.
So you
Yeah,
don't
by,
have the option. I mean, the more intuitive thing might be to scale down. You sort of imagine you're putting a very small ALE, but that would make the Kähler class very small.
That's why
Yeah,
Yeah.
But
so
it's a continuity argument, so it's non-perturbative, right? As you were saying.
yeah, precisely.
I mean, you're not trying to get that.
So usually what you do is adjust the parameters in a perturbative argument to have a small piece here and to have something quite innocuous here, not but inoffensive here, and then you correct with an implicit function theorem. And as I'm planning on using theorem B, which allows any data, you just need some control at infinity of the rate of decaying, but you don't need a fixed global size, say. This allows this kind of brutal construction. So let me sum that up into this. ALF gap non-perturbative argument. All right, and from this asymptotics you can already extract then the volume form of omega m is asymptotic to that of Hm, which was the Euclidean volume form, which is asymptotic to omega g0 volume form. So now what you want to do is to correct omega m and omega m, yeah, in the same Taylor class, so as to give it the precise volume form of omega g0. And then once you have your Ricci flat metric, you just undo it with the other two untouched Kähler forms, and you have your full hyperkähler structure. But at this stage you cannot, if you take the statement with all the details, you cannot apply theorem B yet. So you need to improve a little bit the asymptotics of not of omega itself, but in this chain, which means that you need a better f to work with. If you write down the f popping up out of this relation, you won't have the sufficient asymptotics to apply theorem B. So step 2. So there is a first step into so here with fixed m you correct omega m into omega hat m, which is now with this shape, which is Ricci flat outside. Which is Ricci flat, meaning that it has this volume form outside a compact subset. And the size of this compact subset can vary a lot, but you just need to have this as you want to improve f near infinity. You just need to kind of have good equations near infinity. So you lose a little bit in the asymptotics, but you still have omega hat m minus omega h m equals big O of rho minus r minus 2 minus delta to order 2 alpha in terms of Hölder norms, where alpha and delta are some small parameters. But this is still not enough, because now you have a good f, but you need your metric to resemble a bit more to the model. you need more a bit more regularity. And so this would be step 2b. To apply theorem B, finally, you draw some regularity from the following process. You put G hat m, which is the metric associated to omega m hat, in Bianchi gauge with respect to Hm at infinity, near infinity. And from this you can really draw sufficient asymptotics. This can be made much more precise, but this is really the way to follow. You can draw the sufficient asymptotics and irregularity in order to apply your theorem B and then conclude with a Ricci flat metric, correct GM in the same I1 Keller class. Theorem B. So this was sort of the easy case when the two complex structures on the model and on the gravitational instanton coin were the same from the beginning. So now when you only have a deformation, so yeah, it's a deformation of your Kleinian resolution, say. You can actually do the same, but the price to pay is to make some corrections at the beginning of the machinery, and you need your starting corrections. I mean, you can make them only if you have some you need some explicit you need to know explicitly this term to make pre-gluing corrections. And yeah, so this is also a good game of computations to compute this, and this only makes sense if you have once more a map, a chart between your two infinities. But this somehow natural chart is also given by Kronheimer's construction. So you can work with this this chart. It's a quite nice chart, and then compute this term, or at least the dominant term.
So you're looking at expansion at infinity of how the complex structure differs
Yeah.
from the.
But you actually, to say the truth, you also need to compute the difference between the symplectic forms. The three symplectic forms, the difference between the ALE structure and the Euclidean structure. Just the first order. And for decay singularities, the second leading term is vanishing, which would be wrong for cyclic singularities. And then the third term is small enough to work with. Similar program. And another part of the bill is also you might require a rotation on your hyperkähler structure before starting, in order that some annoying error terms that you wouldn't, or at least that I don't know how to get rid of without this trick. So yeah, with this rotation, you can bypass this difficulty. And that's it for theorem A. And so now a few words on theorem B. So the classical method to solving this Monge-Ampère equation is to use the continuity method. So this goes back to Calabi in the idea of such a method. It goes back to Calabi in the 50s. So you won't solve. Recall that the equation was this. And so the naive idea is to interpolate for the right-hand side member from a trivial right-hand side member, say omega y squared, to the right-hand side member you do want to reach. And this you do by putting a t parameter here. So solve with t in between 0 and 1. And of course, for t equal to 0, your equation is perfectly trivial. And with prescribed asymptotics. And what motivates this idea is that when you linearize the problem at t equal to 0, you have to essentially to inverse a scalar Laplacian, which is usually a bit easier than directly try and solve such an equation. And this observation at the level of the linearized operator remains valid for any fixed t, actually. So to put things a bit more formally, what you do is as follows. So you consider the set of parameters for which your equation star t is solvable, in the sense reducible. So you want to see it's the full 0-1 interval, so you know 0 is in this interval, is in A. You know it is open by invertibility of the Laplacian, as I sketched before. So amounts to invert a Laplacian, scalar Laplacian in ALF geometry. So this was initiated by Vicard and Minerve. So they did it in some L2 weighted space, but once you can do it in L2, it's there is not much difficulty into doing it between relevant Hölder space and then get your solutions. And now about the closeness argument, and this is usually the hard part. Yeah, you need this can be interpreted into saying that when t gets to some limit point, you want this t infinity limit point to be in A, which means that with the corresponding solutions phi t, you will need to extract some limits. So basically, you need some compacity properties of the solutions of your equation, which analytically can be translated into proving a priori estimates. And so you start with a C0 estimate, and what I did was inspired by what Yao did in the compact case back in the 70s, and also by Daniel Joyce, who considered the same equation but now in A geometry in the late 90s, early 2000, yes, 2000. So yeah, this really uses a similar game of integration by parts in order to get this C0 estimate plus, and this is going to be my conclusive remark, an ad hoc Sobolev inequality embedding that can be written as U for rho minus 1 vol. Yeah, it's smaller. I don't know anymore. U for rho minus 1 vol is smaller than or equal than du squared vol. So you know this would be impossible in a non-Euclidean geometry. You have to correct it with some weight function. The good weight is this rho minus 1. And then, of course, you need a square. And with that, you're good to run your integration by parts and reach this C0 estimate. The higher order estimates are done in a more classical way and really rely on this very particular C0 estimate. Thank you very much.
So if I understand correctly, you actually, all of the solutions you produce are as complex symplectic manifolds exactly the same as the ALEs. Is that right?
Yeah. But with this, you need to take into account the rotation in the hyperkähler structure.
But then you can rotate back.
But you kind of break all the when you have to rotate back, you break everything. You just preserve the classes. But you kind of mixed all this Euclidean or ALF.
I see. So you know that for some choice of complex structure, it's complex symplectically standard.
Yeah.
But you don't know that maybe for your original complex structure there might be. But as complex manifolds, they're always the same. You know that. Again, I guess you have the same problem. It's always, you just know that there's some complex structure for which it looks exactly like an ALE.
Yeah.
With the standard.
Yeah. Maybe you can do something there with this to get rid of this to interpret this rotation in terms of deformity. Oh yeah.
So you said that for like the C3 estimates, it just goes the same as basically the same as in the compact case, but there's some new idea you need.
Yeah, it's much more like in Joyce's. It's very close to Joyce's arguments. You just need some decay at infinity, and yeah. So there is a C0 weighted C0 estimate, which is also quite intense. But once you have the weighted C0 estimate, you really can apply Joyce. Yeah. At the end, to run the final, there is a final bootstrap argument as well, for which you need to kind of unfoil your manifold at infinity and to put things, to see things a bit flatter than they are. But this is, the essential game is at the level of the C0 and C0 delta estimates.
Along somewhere in the talk, you said something about more precise things in in one of the limits where the mass is.
I can't hear you, sorry.
Somewhere in the middle of the talk, you said something about more precise gluing was possible, or you thought it was possible in the, say, large mass limit. Is that what you were?
Yeah, I mean, if you follow the gluing by Bicker and Minerd, I think you can read back the limit, just as it's shown in Arezzo-Packard first paper. We can really see the first limit back. So I guess you can get that. I haven't done the exercise, but I think it's you can do it.
I mean, this isn't at the level of rigor of your talk, but my understanding is, I mean, the ALE manifolds have moduli. So, are you getting a model for part of the moduli of the decay gravitational instantons?
In the ALF case, at least you can see the size of the number of parameters, which can be read to describe the construction, which can be read into in the Keller classes. I mean, in the ALE case, these are the exact parameters of the moduli. Yeah. So that would be a kind of that would be I think the family were the good parameters to.
Can you control these classes as you do the gluing? Can you? If it's perturbative, then these classes wouldn't change much. Can you control?
Yeah, I just fixed them at the beginning.
And they don't change at all?
No.
Oh.
But I just correct my first Keller form inside the same class, and I leave the other two untouched. So.
You still have one extra parameter that you don't see in the ALE case because you have the mass. But I mean, just in terms of the linearization of the problem with some fall-offs, can you check that that's the right dimension for the modulus?
Yeah, I guess. I mean, you can also play with some some scaling, but it's the same as.
When you solve the modular pair, you change the size of the cycles. I mean, a priori, it's not clear that they stay the same.
Of the?
When you solve your modular
yeah, but asymptotically, I mean, your solution is really close to the original. In phi, you have you derive twice, so phi is DDC phi is decaying as -2 minus beta already. So this is really close to omega y, and you don't do much on the asymptotic geometry. So this is why you need a very good F to start with.
If you start from the ALF decay, dihedral ALF, can you get the dihedral ALF? Do the reverse construction?
I'd like to, but so far I can't. Because, this is still related to this gap between those two geometries, ALE and ALF. Point that error terms in ALE geometry are manageable in ALF geometries if it's understood by via Legrand's ansatz for retardant. But the ALF error terms back into ALE geometry are really an horror. So yeah, very terrible.
There is a different model for the spaces when k is greater than 3.
Yeah.
You take 2k minus 3 centered multi-tailed nut and position centers symmetrically with respect to z2, and then divide by that z2 action. Is there a way using these techniques to see that these two models are the same? They have to glue to Iguchi Hansen instead of.
Yeah. probably would have to run the same construction in the cyclic case, and then do your do this identification, yeah, and gluing again, which is a little work again, but
Way to see that.
I mean, yeah, in the big lines, yeah, but if you really want to do this, I think there is a little work there. But this can, I think this can be done.
I mean, there are
And
these concrete models for the twister spaces.
Right, on the left, yeah.
And so, I mean, you should be able to read off directly what the various complex structures are. I mean, you just need to check that this is the same metric. You should just find some, I mean, you do know what the twister projection is, and these are fairly specific, you know, very concrete.
From the level of twistor space, we also see this correspondence that ALE is degenerated to that the ALF degenerated to ALEs and have the same complex structure in each fiber.
So you can get it on the nose that it's actually the same complex structure as the corresponding unit.
Yes, yes. But
So then that
we can say something about the metric, the scalar potential. And
yeah. Well, then that should lead to a proof that it's the same, exactly the same metrics. I mean, there's also this paper of Xusheng Chen and Gao Chen, which I have not tried to read yet.
Yeah.
But they claim to have a uniqueness there, and given just some, you know, if it's ALF and it has, I think, curvature that's better than quadratic.
as far as I understand the paper, they don't come with a classification, but they build some holomorphic, interesting holomorphic function. Yeah, playing some weighted analysis, which could help into a classification, but that's to my knowledge what they did. Maybe I haven't read the paper completely enough, but I think that's what
Actually, I'm thinking of announcements. They've got papers that are coming.
yeah.
Yeah. Wait and see what happens.
I think we had enough questions, so let's end this.
Thank you very much.